Hi, we're the Greenville Girls, and we are excited to present our project, Cymatics in Space. We are an informal after-school science group that meets to work on STEM activities.
We are members of Junior RTC who became interested in resonance after learning that soldiers break rank when crossing a bridge. This is to prevent the bridge from reaching its resonant frequency. We started investigating standing waves on a colloidal plate.
Next, we studied standing water waves on a speaker. The study of visible sound and vibration is called cymatics. We took the grill off a waterproof speaker and linked it to a tone generator app. We were able to observe standing waves on the surface of the speaker at different frequencies. Because of our interest in space, we wondered what would happen to resonating waves in microgravity. We constructed a payload and dropped it from our homemade drop tower. We had a wireless speaker linked to a tone generator and a sports camera to record the results.
Here is one of our many drops. After the drop, we slowed the video down and analyzed the images in normal and near zero gravity. We were able to determine the moment of microgravity by watching the air bubble in a level. When microgravity is achieved, the bubble becomes a sphere in the center of the fluid.
Here are some of the images. We all agreed that the images looked different. In near zero gravity, the waves looked taller and more defined. We wished we could have had a longer period of time to study the resonant waves in microgravity. We decided to enter our project in the Possum 13 International Microgravity Challenge in order to have longer exposure to microgravity conditions. We hoped we could get quantifiable data to support our hypothesis that resonance will occur at the same frequency, but the standing waves will be taller and more defined.
We went through multiple designs and prototypes in order to meet the challenge constraints. Several of our designs involved using parafilm, petri dishes, and pods made of bubble wrap to contain the water. Our recording prototypes included a sports camera, endoscope, and handheld microscope. We designed a PVC pod payload which keeps the fluid enclosed. A wireless speaker was linked to an Android's tone generator app, and a wireless microscope was used to magnify and record the data.
A Hobo Data G monitor is attached to the pod to record information on the G-force of the payload. After the flight, the information must be saved with the computer program. Because there may be an opportunity for more than one parabolic cycle, we made mixtures of different density using PEG. A different density liquid can be analyzed on each of the cycles.
We determined frequencies of resonance for each of the fluids and made a spreadsheet to be referred to during the flight. This is our final design. The control operator will have a control panel with Android devices linked to the microscope and tone generator. The different density fluids are in capped syringes that can be injected onto the speaker. Everything's velcroed to a clipboard to keep it from drifting during the flight.
The control operator will record each cycle through the predetermined frequencies during the flight. These will be compared to the video made on the same density fluids in normal gravity conditions. On the right, I am changing the tone frequencies, and on the left Android shows the recorded standing waves. We have tested our project and it is ready for flight.
We can't wait to receive and analyze our data. If our data is promising, we will try to have an even longer exposure to microgravity, maybe even on the International Space Station.
We would like to thank
Possum 13,
NRC, CNRC,
Master Sergeant Durden,
and Joe from Lowe's.